All right, we're going to get started here now. So it looks like we got about 8 people, looking good. So I guess just a little preface just before we begin. So if you're an aerospace engineer or mechanical engineer, and also, let me know if anyone can't hear me or anything. If you're an aerospace engineer, um, you should, you'll take every class that we talk about except for heat transfer. If you're doing a minor in mechanical engineering, you will most likely take it. But if you do have an elective, I highly recommend you take heat transfer. You'll use it, and it's used in almost every single aspect, and especially if you want to work with rockets or space, it's huge. So that's just one thing I want to start with. If you're a mechanical engineer, um, on the opposite side, you should take all these classes except for compressible flow. Again, I highly recommend taking compressible flow. If you don't really know what the difference or what compressible flow is, that's all right. We'll talk about it during this lecture. But I highly recommend you take it if you have the space. So again, this is an introduction to the thermal sciences. If you don't know me, my name's Liam Nestor. I'm the VP of projects. And if you're asking why am I qualified to teach this, I'm a graduate student, mechanical engineering, and my focus is in thermal sciences. The research I'm doing right now is I'm doing research in complex channel design and analysis for nuclear thermal propulsion methods. So it's another type of propulsion used in space, and all the stuff in here I use on a daily, either in calculations or in theory. So here we go. Okay. So, we're going to go through some thermodynamics, some fluid dynamics, and some heat transfer. Again, these are all classes that you will most likely take. The fluid dynamics is going to break down into compressible flow and incompressible flow. We'll talk a little bit more about that. And again, I'm just going to reiterate, if you're aerospace, I recommend taking heat transfer too. If you're mechanical, I recommend taking compressible flow as well. So we're going to start with the thermodynamics. Thermodynamics is the relationship between heat and other forms of energy. So for most of our problems, we're going to assume that the medium or the fluid that we're working with is an ideal gas, which means it follows the ideal gas law. It's incompressible, and we'll talk a little bit more about what incompressible means. And it moves in a 1D or quasi 1D flow. One dimension is obviously moving, left to right or up and down. Quasi 1D is there's a bit of a 2D action going on, but we just assume it's moving in a 1D action. So this is the ideal gas law. On the left, that's probably the form that most of you are familiar with, PV equals nRT. On the right, this is the form that most aerospace and most real engineers will use. It's just a relation between different states that you're going to find your gas in or your fluid. And this allows you to calculate to find out what state it's in. It's really useful. You're going to use it a lot. So these are the different laws of thermodynamics. A lot of the time, they're very straightforward. So we'll just kind of go through them. Also, the zeroth law just states that two systems in equilibrium with the third state are in equilibrium with each other. Another way to kind of think of it is if A is in equilibrium with C and B is also in equilibrium with C, then A is in equilibrium with B. And when we're talking about equilibrium, we're saying that that they're all in the same state. They all have the same properties and whatnot. The first law of thermodynamics, change in energy of a system is the amount of energy added to the system minus the amount of energy spent doing work. A really easy way to see this is if you have a pot of water boiling, or if you have a pot and you'd fill it with boiling water, instantaneously, you are going to lose some of that energy to heating the other elements around, the pot, whatever it's sitting on. And then so the energy is added and then the work is taken out and it's used to heat the different aspects. The second law is entropy of a closed system will either remain constant or increase. That's a major law of the universe. Entropy is one of those things kind of hard to explain, but the way a lot of people explain it is it's the amount of measured chaos. Kind of a cop-out way to explain it, but essentially this is just saying that systems cannot be reversible. So, heat moves from hot to cold. Unless you put work into it or some sort of energy into it, you're not going to get heat to move from cold to hot. And the third law is it's impossible to reduce any system to absolute zero in a finite series of operations. So essentially that's just saying you're never going to be able to reach 0 Kelvin. It's just impossible with the technology we have. And according to thermodynamics, it's impossible to get. I think there's some labs either in like high mountains or maybe on the ISS, they've been able to get like 0.2 Kelvin, maybe 2 Kelvin. That might be wrong. So don't quote me on that. But I know the average temperature of space is about 2.7 Kelvin. So even space isn't temperatureless. So this is, if you've taken Engineering 103 or heat or thermo, this is kind of one of the first equations that they present with you. It's just the energy equation due to heat. So Q is your energy, the mass of the system. Sometimes you're going to see this equation with a lowercase q equals C sub P delta T. Usually when you see a lowercase letter, that just means they've taken mass out of it by dividing the mass over from the right to the left. That kind of allows the system to, or that allows the math to be a little bit easier, especially when you don't know your mass, or you don't know it until the end, which is fine. It just makes the calculation a little bit easier. So down here, I talk a little bit about the specific heat capacity. So you have a specific heat due to pressure, and you have a specific heat due to volume, which you can see at the bottom. Here's the relation between the two. And, our specific heat due to pressure is calculated by the change in enthalpy over the change in temperature. Finally, another huge relation, especially if you're an aerospace engineer, you're going to see this all the time, is this gamma. Gamma equals it's called the specific heat ratio. If you're a mechanical engineer, you're going to see this a lot in your upper level heat classes, but especially you aerospace engineers, you're going to be seeing this really soon. This is a huge relation, and you're going to see it a ton throughout this presentation. And also, if you have any questions or anything, feel free to chat me or reach out or do whatever. So, you might be sitting there wondering why is all this stuff important? Well, it's super important for a lot of reasons. Propulsion's a big one. Most propulsion methods that we use today are combustion oriented. Thermodynamics is highly used in combustion because you need to know, especially in the calculations, the design, the analysis, all that, you need to know what state your combustion products are in and all that stuff. You need to be able to use thermodynamics to figure out temperatures in different areas so you can use the proper materials and whatnot. So if you're not very sure of how overall combustion kind of works, it takes chemical energy, makes that chemical energy, combust or go boom. It releases different products and in the form of gas usually. And then that gas is translated into kinetic energy to create thrust. So from a rocket nozzle, for example, you have, a fuel and oxidizer. They get pumped into your combustion chamber. They combust. They create gas. And then they go through a nozzle to expand, creating kinetic energy, which creates thrust. Cryogenics, if you're not really sure what a cryogenic is, that's fine. All it really is, take, nitrogen, for example. At room temperature, nitrogen is, or at standard temperature and pressure, nitrogen is a gas. But if you bring down the temperature a lot or you increase the pressure a lot, you are going to transform that nitrogen into a liquid stage. Once it reaches that liquid stage, it's considered a cryogenic, and it's very, very cold. There are a lot of benefits of using cryogenics for space applications. Probably the biggest one is you could store your fuels, and they store their fuels cryogenically because you can pack a lot more of your fuel into there. And, from a cryogenic standpoint, you can actually kind of see this from the gas relation. So if you increase your pressure a lot and your density is going to change, but we'll just assume it stays constant, and your specific gas constant is not really going to change. Well, actually, no, that's not true. This is a bad example. Don't worry about it. So the next thing we're going to talk about is fluid dynamics. So fluid dynamics is the flow of fluids, liquid and gases. So for the first part, we're going to assume incompressible, and then we're going to talk a little bit about compressible fluids. So a common definition for a fluid is anything that fits its container. If you have a rock and you put it in just like a plastic Tupperware, it's going to stay rock. If you pour some water in there, it's going to take the shape of that container. So again, we're going to go through some applications of the fluid dynamics. Flow through pipes. You're going to be answering questions like, how quickly will the propellants flow through the pipes? Or how big do we need the cross-sectional area of the pipe to be to reach a certain flow? Nozzle flow, that's where you're going to see your, at least for a rocket perspective, that's where you're going to see your compressible fluids knowledge come in. So how quickly does the gas leave the nozzle? How quickly does it need to attain a certain level of thrust? And then finally, another big example is drag on a structure. We all know if you're driving a car and you put your hand out the window and, you make it perpendicular to the direction your car is going, your hand's getting blasted with all that air. But if you turn it and it's going parallel with the car, it decreases the amount of drag. So that's another very big example. So kind of here's where we're going to talk about the difference between incompressible and compressible fluid. So does my density change? If it does, it's a compressible fluid. If it does not, it's an incompressible fluid. So if an external force is able to change my density, I am considered to be compressible. And if it's not able to change my density, then I'm considered incompressible. Traditionally, compressible, we assume a fluid is compressible when it's greater than Mach 0.3, and we consider it incompressible when it's, that's supposed to be a less than sign. I apologize for that. But it's supposed to be incompressible when it is slower than Mach 0.3. Maybe not this presentation specifically, but when you take these classes, you're going to quickly find out that incompressible fluids are way easier to deal with mathematically than a compressible fluid. So a lot of this presentation is going to have some very complex things in there. Don't worry about the math and that stuff right now. I just wanted to put that stuff in there so you're familiar with it when you come to see it. So I'll put a complex version in there, or kind of like the actual way of how the real equation's written. And then I'll kind of simplify it for the purposes in which you'll use it in here and in classes. So this is the conservation of mass, also known as the continuity equation. So all the continuity equation is saying is the increase in mass is equal to the mass in minus the mass out. Extremely simple. You probably did it in your high school physics class. So as an undergraduate student, there's probably about a 95% chance you're never going to deal with a term like this. This is a transient term where things change with time. Luckily, that makes things a lot easier for you. Again, like I said, don't worry about the math and symbols and stuff. This is called a gradient. I'll talk a little bit about that in the next couple slides, but this equation can be reduced to this equation. So the mass in, the mass in is equal to the mass out. This is the mass flow rate in this specific example. And this is just the equation for mass flow rate. If you're just doing a pipe and your area doesn't change, well, then if your area doesn't change and your density doesn't change in your fluid, well, then your velocity is not going to change. If you're doing a nozzle for water, for example, and your density doesn't change, but your area does change, then your velocity is going to change. It's a really simple relation between the two. One big thing to remember for the simple version is that this is only true for an incompressible fluid. This can be used for a compressible or an incompressible fluid, but this is only true for an incompressible fluid. So this is the conservation of momentum. So, if you're really about thermal fluid stuff and you know what the Navier-Stokes equation is, that's great. If not, you're looking at it right here. A little fun fact about the Navier-Stokes equation is that it actually does not have a characteristic equation. And in, I believe, 2009, maybe, it was listed, or 1999, I can't remember, but it was listed as one of the top 7 mathematical relations to be solved in either the century or the decade, whatever year it was for. So there's no solution to it. However, what we can do is we can break down the solution, and we can make a ton of assumptions to make things easy. So as I talked about, actually we'll see it on the next slide what this gradient is. But one thing I did want to talk about is this term right here, this dv dt. So this is called a total derivative. If you haven't taken calculus yet, don't worry about it. Just a little background on it. So there's three kinds of derivatives: total, partial, and Lagrangian. A partial, the easiest way to describe it is kind of through this metaphor. Imagine you're on a boat in the water. And there's fish throughout the water and stuff like that. If you want to sit your boat in one spot and count the number of fish that go in a certain area, that would be considered a partial derivative. You're only looking at one specific area. And what you take the partial derivative of your equation, that's fish going through that area, and that will give you that answer. If you want to look at the fish in a column of water, that would be more of a Lagrangian derivative. And if you want to study the fish in the entire ocean, that's your total derivative. So your total derivative is going to take into account the change of your function with time, with all three of your Cartesian coordinates. This is just the Cartesian total derivative example. And here, another thing to point out is when you take the total derivative, you're going to be multiplying in the fluid velocity vector here. It's not really important. A lot of the stuff is just kind of stuff you don't need to worry about. But again, I just want to put this in there because this is what the real stuff looks like. You may or may not come across some of the stuff when you're studying it. I can't really tell you, but to put in terms, so the rate increase in momentum is equal to the rate of momentum in minus the rate of momentum out plus any other external force on the fluid. So this is essentially what we're looking at is a force balance on your fluid. Quite simple in those terms, but the math can get pretty complicated, as you can see. Another huge equation that you're going to use all the time is Bernoulli's equation. For this one right here, this is just taking a pressure balance in between one area and a pressure balance in between another, and allows you to solve for any one of these variables. This can also be rewritten in terms of velocity by just moving some terms around, but it's all the same thing. For this equation, again, this is assuming incompressible 1D steady flow. As you can see, there's no derivatives in here, especially no derivatives due to time. And this is assuming no viscous forces. So moving into the compressible field, when you have compressible fluids, you are going to encounter things called shock waves. Now, there's three types of shock waves: oblique, normal, and a bow shock. As you can see here, this is an oblique shock. What's going to happen is it usually comes when you have a really sharp angle, like you can see right there on the tip of that plane right there, or right here on this diagram. You have a hard angle. It's not blunt like right up in here. So you're going to have a connected shock wave as it's connected to the tip, and that's an oblique shock. A bow shock is kind of what you're looking at right here, except if this was blunt, it would be like a very similar thing, but it'd be bowed out instead. And then you have a normal shock, which is going to happen when your Mach number reaches or is greater than 1. So your Mach number becomes greater than 1, it's going to bow shock, and then it's going to continue it's going to normal shock, and then it's going to continue doing that all the way down. This is really important because we need to be able to calculate what's going on behind the shock wave and in front of the shock wave. So as you can kind of see here, this is just kind of a large mess of flow characteristics and general compressible relations. So kind of going in specific order here, you can kind of see down here, this is our Mach formula. So this is the Mach number. It's the velocity of your fluid or your object over A. A is the speed of sound. Whoops. Don't know how that happened. Oh, whoops. A is your speed of sound. And your speed of sound is calculated by that gamma RT. That gamma, like we talked about earlier, is the ratio of your specific heats. Now, a lot of these other ones, especially, so these three right here are kind of what we just talked about. These are the temperature relations between Mach waves. So this T naught, you can see down here, is a stagnation property. So the easiest way to picture that is, imagine if all the energy in your system was in the form of heat energy. That's a stagnation property. If, whatever your pressure, internal, whatever it might be, it just all is lumped into a temperature, that's a stagnation temperature. And we can use this relation to calculate what's going on before and after Mach wave. Quite simple. This is the temperature before the Mach wave, and this is all the properties before the Mach wave. Then you calculate it for the end. And then if you have another wave and you want to calculate it, you just do the same thing over again. So this is the relation for the temperature, the density, and then the pressure. And again, look at all these gammas. They're really common. Finally, these are your isentropic relations. Isentropic just kind of means there's no losses in any way from heat, flow, none of it. Again, here's your gammas, and these are really useful for doing nozzle calculations. But that's kind of something we'll talk about in another PowerPoint. The last thing I kind of want to talk about is the flow regimes. So subsonic flow would be anything from a Mach number from 0 to 0.8. Transonic would be a range of 0.8 to 1. Supersonic would be anything from a Mach number of 1 to 5. And then hypersonic would be Mach numbers from 5 to infinity. A really big topic right now in the aerospace world, especially in defense, is hypersonics. The U.S. military is really trying to develop our hypersonic missile capability. There's tons of companies out there working on it. If it's a defense company, it's doing something with hypersonics. It's a huge field. If you're interested in hypersonics from a not defense point of view, it's also used in space exploration. Re-entry vehicles, you reach insane Mach numbers. And with that, you need to be able to calculate these temperatures, and they are extremely high. So the next thing that kind of leads us to is the heat transfer. Heat transfer is a subset of thermal engineering that concerns the generation, use, conversion, and exchange of thermal energy. If you've ever burned yourself, you've experienced heat transfer. It's very simple to think about theoretically, but the math can sometimes get a little crazy. So some of the applications of heat transfer, I mean, you all know what heat transfer is, but, motor casing heat. When you have a propellant and it's burning in your motor case, you need to know how hot your motor casings get so you can adequately use the proper materials. Cryogenic propellants, we talked about earlier. You're going to have extremely low temperatures. Like, I think cryogenic liquid nitrogen is, negative 329 degrees Fahrenheit. It's extremely cold. It's around 70 Celsius or 70 Kelvin or something like that. I forget. And then again, like I talked about the motor heat, the material selection. That's huge with the thermal stuff. You got to know your temperatures in different spots so you can adequately select your materials. So again, like I did earlier, this just kind of going with the big equation. So this is your energy equation. It's not as daunting as it looks. In this form, it does look kind of daunting, but here it's quite simple. So as you all probably know, there's 3 forms of heat transfer: convection, conduction, and radiation. I probably should have put that in here, but convection is heat transfer through some sort of medium, so through a liquid or a gas usually. Conduction is heat transfer through 2 rigid body objects. And you can actually see that in this equation right here. So these terms right here would be your convection terms. So, this velocity refers to whatever your fluid velocity is. This group of terms right here refers to your conduction. And there's nothing in here for radiation, but we don't need to cover that now. And right here, this is just some property-based stuff. And this is a transient term for your change in temperature with the change in time. As an undergrad, 9.9 times out of 10, you are not going to worry about this at all. You're going to have this equation equaling 0. If you're wondering, this equation is called viscous dissipation. So the easiest way to describe that is if you have a big pot of fluid and you're stirring it, technically by stirring it, you could be creating heat, internal heat in there. So this term just kind of encompasses that. A lot of the time that term's left off, nothing to worry about. So this is the governing law for heat equations. It's called Fourier's law. If you're going to see that a ton throughout your stuff, so don't worry about that right now. Probably the biggest thing about this section is the types of boundary conditions. So like I talked about, you're going to have conduction, convection, radiation, all that stuff. But your surface boundary conditions can be anything. So for example, if you have a temperature here, if you have a long rod, and on one end of that rod you're putting a temperature, as you go down that rod, your temperature is going to decrease. If you have that rod sit there for 1,000,000 seconds, you can go to the end of that rod and probably touch it, and it shouldn't be too hot if it's long enough. If you have a heat flux, though, that's a constant stream of heat going into that rod. So it's going to trail off similar to the heat once you get to a certain length, but you're going to have a constant heat flow into that. If it's insulated, you don't really have to worry about that one. That's just kind of saying that there's no heat transfer at one point of there. Nothing's truly insulated, but a lot of things can be modeled as insulated to make things simpler. And finally, convection. Going with the rod example again, if you have a rod that is instantaneously put at 50 degrees Fahrenheit and you submerge it in a fluid that's 1 degree Fahrenheit, that's your convection. All the heat from the rod is gonna start to reach an equilibrium with the fluid around it. So that's pretty much it for this presentation. I know it's probably a ton to take down, and I know it's probably not super useful from a mathematics standpoint. This was mainly trying to serve as like a kind of more like giving you the theoretical background behind this stuff, so that way when you get to these classes or when you start solving these problems in the org, you have the theoretical background, because we're engineers, we can figure out the math. That's not the hard part. It's understanding what's going on. So I'll be here for a while. If you have any questions, feel free to reach out. There is a question that I missed, but no question. But if you have any questions, feel free to speak out. That's pretty much all I had. I'll be here. I can answer questions about, the specific topics, anything in the club, or anything kind of aerospace in general. So, if you don't have any questions, you're free to go. Thanks for coming, and I hope you learned a little bit. This will be posted and sent out like normal. So just keep your eyes out for it. Thanks, guys.